That's fine. So I will speak about recent findings from the summer 2013 intensive monitoring campaign. My co-authors are Xiaomeng Li and Jeff Brook, who are both senior scientists at Environment Canada, who really were the scientific lead behind the results that I'll show today. But it's a large team, like many of the other presentations. There are a fair number of research scientists and research support staff and supporting organizations that helped us undertake the measurements and the results that I'll talk about today, and they're all listed here. So I'll talk for a moment about what the objectives of the air component of the Jocelyn program were. I'll spend a few minutes talking about cumulative impact assessment, because that's really an important concept. And then I'll give a brief overview of the airborne measurements and some results, a brief overview of the ground-based measurements and some results, and finally the next steps in this analysis. So this slide has been shown before by pretty much every component. From the air component perspective, the overriding objectives of Jocelyn were to determine what's being emitted into the atmosphere, how is it being transported in the atmosphere, how is it being transformed chemically, and where is it being deposited. And if you can get all of that, then at the point of deposition or ambient, you can then perhaps assess cumulative impact assessment, and I'll speak to that in a moment. So the summer intensive campaign was a measurement campaign by a fair number of researchers from a fair number of organizations, designed to integrate data from a wide variety of measurement platforms and sources, including two very intensively instrumented measurement sites in the heart of the oil sands region. One at Wabia Site 13, which is in the forest, sort of equidistant from Syncrude, Suncor, CNRL, and Shell, and then a second site in the Fort McKay community. So two intensive ground-based measurement areas, and a research aircraft that was fully instrumented for measuring pollutants. Integrated with that were satellite measurements and a numerical weather prediction model, and collectively we tried to assess the full range of pollutants in the oil sands region during the time of the study, and I'll talk about some of that. This is pretty much the same slide. It just shows a picture of one of the measurement sites with the research aircraft overflying it, and I'll give some examples of that in a moment. So this is a really important slide because it answers the so what that's been talked about several times today. So if you take an arbitrary species A and there's a source of A into the atmosphere, the meteorology is really the process which transports it in the atmosphere. Chemistry is the process by which A transforms to B through a chemical reaction. And ultimately, both A, the original A, if it's still in existence, and B, its transformed product, represents an exposure at the surface somewhere downstream. So we give the different processes names, so emission, transport, transformation, deposition, and ambient. And my group in Environment Canada is primarily responsible with trying to measure these processes. So we spend a lot of time trying to measure correctly or accurately emissions, trying to measure the meteorology, measure the chemical processes for the chemistry, and then measure the deposition processes for deposition. That's done in order to understand. In all four cases, we want to understand the physical and chemical processes that are driving those pollutants. And if we can understand, we can define. And define is really the numerical parameterization of those processes in a way that we can incorporate into a numerical prediction model. And so it's key. The numerical prediction model becomes the tool whereby all of that information is incorporated. And so just to go back, my group primarily focuses on measure and understanding, and then leading to define. And there's a sister group in the organization, which Heather will speak to in a moment, which does define, development of the model. Once you've got the numerical prediction model, that is the tool by which you can assess air concentrations and deposition everywhere, continuous in time and space. That is the tool you need to get to cumulative effects assessment. And of course, you could integrate at that point with water, with hydrology, with ecosystem, with whatever other models are out there, and it's the integration that gives you fundamentally cumulative impact assessment. So I talked about how important the model was as the tool for integration, and when we came out to the oil sands in 2013 to make the intensive measurements, we already had a numerical model which was able to make predictions of different chemical species. And so this just gives you an example of what it was capable of at the time. So measurement of plumes downstream in the oil sands region for SO2, NO2, xylene, PM2.5. It's not to say that the model was correct. It had, at the time, the best physical and chemical processes incorporated. But we used those kinds of output to guide where the research aircraft would go to validate the model and perhaps improve the processes that were in the model. So this is a picture of the aircraft. You can see the inlets on the top from which fed all the gas and phase measurement instruments. At the front of the aircraft were inlets for aerosols to measure the particles, and under the wings were other aerosol probes for measuring the aerosols and particulate matter. Pretty much able to measure the full suite of gaseous VOC compounds and particulate compounds that we could find in the atmosphere, excluding things like PACs, PAHs, metals. We couldn't measure those with the aircraft. This is a picture on the inside of the aircraft. On the right side, you see all the racks of instruments for measuring gas phase, ozone, SO2, NO2, etc. On the left, you see all the mass spectrometers for measuring VOCs, acids, and other gaseous species. Collectively, we could measure the full suite of pollutants. So here's the methodology. Take a facility, and the facility that's shown here is Syncrude, but it could be any facility, and draw a rectangle around it. And we call this the box model because the rectangle represents essentially a giant shoebox. And we fly the aircraft around each side of the facility at different altitudes, from the lowest altitude starting at 500 feet and then working up in 250-foot increments or whatever increments were needed. Usually it was about 250 feet, so to 750, 1,000, 1,250, 1,500, etc. And by doing that, we can map the pollutants out of all the things we could measure at all these different altitudes along each of the four walls, the north, the south, the east, and the west. And then once we've done that at several altitudes, we can create a two-dimensional map of each pollutant on each wall. And so what you see in this particular picture is just the SO2 map, and you can actually see the red represents where the major part of the SO2 plume is going out of the northeast or the top right corner of the box. But if you can do that correctly, then you can, the net flux of any pollutant species into the box, subtracted from the net flux out of the box, gives you the net emission inside the box. So you can characterize the entire facility's emissions for whatever your species of choice would be. And so here's just a few examples of where we did that. At the top left is, again, another box flight over this Syncrude facility. Bottom right is a similar flight over the CNRL facility. And the top right, instead of doing a box, we do a series of walls at progressive distances away from the oil sands region, and that gives you transformation. By measuring the changes through each wall at 50, 100, and 150 kilometers, you can get your transformation chemistry. So here's an example. This is looking south at the CNRL facility. This shows one particular aircraft flight on one particular day. The winds are from the north, and so again you can see SO2 color-coded and exiting out the south wall of the facility. If we now translate that into two-dimensional maps of different species, you can see the top left is the SO2 plume as it exits that facility. The top right is the methane plume, and the bottom is the toluene plume. And of course, I'm just showing 3 plumes here, but we could do it for pretty much every species, every VOC that we were able to measure, and particles or particulate matter. So we can really get a strong assessment of what the net emissions from the facilities were for the species of interest. And if you then have a very fine micrometeorology surface level wind model, you can now trace those back and do source attribution. And so we haven't done that fully yet, but just looking at where the wind directions are here, you can pretty much attribute the SO2 plume to the desulfurization unit. The toluene's coming from the tailings pond, and the methane's coming from the mine face and from the tailings pond. So then you could, in the case of, as an example, VOCs, we could compute the total VOCs coming out of a facility for an entire flight. Now these are 3 flights shown here, flight 2, 12, and 18, all around the same facility. The particular facility this day was Syncrude, for these 3 days, sorry. And you can then compute using our mass spectrometers and our canister system that was on the aircraft. You can compute the total amount of VOCs that are being emitted by the entire facility. And you can work it out. You can see the numbers there, 37 tons per day up to 53 tons per day over the 3 flights. So the far right gives you an average of the 3 with an uncertainty. You can now take that number, that sort of 45 tons per day of VOCs, and compare that to the emissions inventories or the engineering estimates or any of the methodologies that George talked about in the first talk yesterday with respect to how you estimate emissions from a facility. And that we can now inform as to whether those emissions are in the right ballpark or not in the right ballpark, and perhaps if not, where are the emissions coming from. So this is another example of the same methodology, but instead of applied to a box flight, it's applied to a transformation. So what you see here are the entire oil sands region downstream. That's the yellow box. The winds are from the south, going mostly to the north. And you see 4 different walls, all at different distances away from the oil sands, up to 120 kilometers away. And what you're seeing on this particular graph is organic aerosol mass. So it's essentially PM1. As measured by mass spectrometers and other instruments on the aircraft. So what you're seeing is the development of organic aerosol, the formation of it downstream. And so what's happening is the whole plume from the oil sands is moving to the north. It includes VOCs and SO2 and NOx and other pollutants. That plume is a reactive environment, and the VOCs are being oxidized and they're forming into secondary organic aerosol. And the formation rates are all shown there. You can estimate the formation rates by the distance or the difference between each wall. So it's not a fair comparison, but to give you a sense of how much is being formed, if we were to take the total NPRI estimates of PM 2.5 from all the facilities in the oil sands, it works out to about 0.86. I can't even see the units, tons per hour, I think, compared to 3.4 tons per hour of aerosol being produced in the transformation processes downstream. So it's a fair amount of transformation of the pollutants as they move downstream. You've got to get that right if you want to correctly understand the transformation and ultimately the exposure or deposition of the pollutants. So the summary of the Airborne campaign, we did 22 flights, all similar to the ones that I just showed you. They were focused on pollutant transformation, satellite validation, emissions characterization, and we characterized every major oil sands facility in the oil sands region. And we're just at the point now of finalizing all the data analysis for all the different chemicals or species that were measured, and then we will use that to help you to get back to work with industry to inform as to whether their emissions estimates are in the right ballpark or not for species for which we have some uncertainty. So similar to the Airborne program, we had 2 ground-based programs where a similar suite of instruments were added. This shows a picture of AMS-13, would be as AMS-13, which is in the woods just south of Fort McKay. We were allowed to modify the instrument site and add a fair number of instruments, again, for measuring all the different gas phase and particle phase species of interest. And then in the Fort McKay community, with the collaboration of the Fort McKay First Nations, we were able to put in a measurement site and put in a measurement trailer there for measuring the criteria or contaminants. And very importantly, 2 remote sensing systems, an upward-looking LiDAR system that could give us aerosol distributions up to 13 kilometers, and a WinRAS system, which would give us a wind profile up to about 800 meters. The WinRAS system and the aerosol system, the LiDAR system, give us the dynamics of the boundary layer, so that when a pollution event is seen with the CAM1 trailer, which is the trailer shown on the left, measuring all the gases and particles, when a pollution event is seen with that trailer, we can then use the LiDAR and the wind profiler to understand, or the WinRAS system, to understand the dynamics of the boundary layer. That tells us how the pollution is being transformed, how it's being brought down from the boundary layer back to the surface again, and we can usually do a back trajectory to do source attribution to understand exactly where the pollutants were coming from. So just one example, and I just want to make the point, we've had this system now in operation for about 1.5 years, going on 2 years. We have an extensive number of what we'll call pollution events in the community, plus the full 1.5 years of intensive data. and we're in the process of analyzing all the case studies and coming up with some ideas about what kinds of pollution events hit the facility and what their origin and evolution are. So just one example. So this was a pollution event that hit the Fort McKay community. You're seeing in the top there a time history of, the yellow is total sulfur, the red line, or the brown line, sorry, is SO2, which was around 50 parts per billion. The red line is total reduced sulfur, which is 25 to 30. So there was a definitive odor, and certainly with a total reduced sulfur, 25 to 30 parts per billion, there's a good correlation with that. But a different measurement system a couple of kilometers away measured the same SO2, but essentially 0 or 1 or 2 total reduced sulfur. So it speaks to the point that not all measurement systems are able to measure all species the same way. And in this particular event, we had 2 different measurement systems measuring total reduced sulfur with very different answers. If we want to inform the monitoring network so that it does the best possible job in all cases, we need to reconcile differences like this. And this has now led to an intercomparison between the 2 systems, a side-by-side intercomparison, in order to try and advance the monitoring's programmability to measure total reduced sulfur in all situations. This is just one little case study of the dozens that we've acquired. So where are we? The majority of the data have now been quality controlled and analyzed. They're being posted to the portal. The results and interpretation are now coming out. As I've just showed you some snippets today, but there's a lot more behind that. Over the next year, there should be probably 6 or 8 papers that describe the detailed results of the emissions and transformation estimates. And of course, most importantly, is that all of this information leads to improved physical-chemical processes, which then get incorporated back in the numerical model, which Heather will speak to in a couple of talks, but which is the central tool for assessing, at least in the air, from my perspective, cumulative impact assessment. So thank you.
Yeah, we do have a few minutes for questions. Anybody go over to this microphone here?
Diane Phillips. I'm a regulatory advisor for Syncrude, and actually I listen with great interest because I've been involved with preparing emission estimates for my site for the last 10 years. So I just have a couple of questions. So I'm fully aware that, let's say with SO2 emissions, there's variability from day to day, and if one of the intentions of your program is to get an assessment of the accuracy with respect to MPRI emissions, my question is, like when you get an annual tonnage, are you going to then, divide it by 365 days and then figure out what it should be on a day, and then if the value is out by a certain amount on that day that you took your sample, assume that the emission estimates are inaccurate? Or how are you going to incorporate day-to-day variability in SO2 emissions from a site? And the other part is, like, how are you going to keep this fresh or green going forward? And for our company, we did bring our scrubber online last year, and so in 2014, our SO2 emissions decreased 100%. So if you go forward in the future, like, how are you going to use this data to assess emission inventories?
Well, we've already been working with companies such as CNRL, for example, and they've given us, minute data that we can then correlate directly with the aircraft measurements, and for SO2 in particular. So our hope is to do similar comparisons of the data with any of the industries that are willing to provide the data that we would require. But as I said, some industries have given us the data, and we can do very, very nice correlations one-on-one. Clearly, if we make a measurement of SO2 around a facility today, and they change their output tomorrow, then it's unfair to do a comparison of today's aircraft measurement with 3 days from now's new technology, right? Clearly, that's apples and oranges. But we can compare apples and apples with respect to what was happening in 2013, simply by working with the industry to get that kind of data from them directly, and
so
we're doing that.
That's encouraging. There's a recognition, I guess there's a need to discuss with industry, I guess, their understanding of emissions on that day to get the right correlation.
Absolutely, and we've been working with CASIA since the first day to try and get all of the different emissions estimates from the industry. And now we've actually got industry asking us for things like CO and methane and CO2 for particular days because they want to test their greenhouse gas emission estimates. So this is going to go on for a while, this back and forth. First, we had to demonstrate we had the credibility to do it, though, which is there. Now we got to go back to industry and get that back and forth going.
Thank you.
Great. Question. Another question there?
Stewart, can you give us an idea of what the cost was for this campaign?
Is that
No,
a,
it's a wonderful piece of work from my perspective and much needed, but it obviously came with a healthy price tag.
Yes, the Airborne campaign itself costs roughly $2 million for a one-month program. But I would argue that with that kind of campaign, I can save you a lot of money in the future by using the data wisely. But that's a whole different talk, and a whole different discussion.
And following up a little bit on Diane's question, you know, things change, and they've changed this last year in terms of Syncrude, implementing flue gas desulfurization on a main stack source. So from your perspective, Stewart, how often do you think that this type of a campaign effort should be conducted?
It depends on what the objectives are. If the objectives are to validate emissions inventories, that's a completely different objective than if the objectives are to develop a numerical model that's capable of predicting, you know, all the chemistry downstream everywhere all the time. It's a tough question to answer very, very directly. But you know, things change. I just give you one example of how good, for example, SO2 is. So we've been working with CNRL. And, you know, we flew around CNRL one day when they had an upset event, and they gave us one number for the upset, and we flew around CNRL a different day when they gave us a non-upset event, was a different number, and the two numbers that they've given us for their SO2 emissions agree with our aircraft measurements within 5 to 10%, which tells me that their emissions estimates, the methodology that they're using for SO2 is excellent. Now, that said, we know it's not so excellent for things like VOCs, and so, you know, I think that we could inform a lot through a VOC discussion, right? A comparison of the aircraft VOCs with industry estimates of VOC emissions.
I think Dan's got a question.
Right. Dan, did you have one more? Yeah. Yep. Okay.
Hi, Stewart. Dan Stuckless. I work for one of the First Nations. You're familiar with them, sure. My question is on the equipment that you've used at the CAM1, specifically related to metadata. And I can think back to one event where there was a significant event in the region where the current towers and metadata suggested that the wind direction and those kind of things were moving a different way when I was standing on the front porch of one of the buildings in one of the communities, and I can see that that wasn't correct. So this is probably more of an Emera question, but what is Emera going to do to make sure that we have that best equipment, that world-class equipment, so that we can have the best data possible? Because I think if we had to rely on not our eyes that night and we had to rely on the wind data, the interpretation would have been that that event would have avoided the community I work for. But in actual fact, it floated completely over and over the Athabasca River. So I'm just wondering what work is underway within Emera, and maybe you can answer that, maybe that's a takeaway question, to make sure that we've got the best possible, not just in the community of Fort McKay, but in other places.
Yeah, I can't speak for Emera. Okay.
They did. Okay.